What if your computer could think like your brain, not just crunch numbers, but actually learn, adapt, and evolve? Scientists have now created chips that mimic the way our brains process information. They don't just calculate, they recognize, respond, and even restructure themselves as they learn. This isn't science fiction. It's called neuromorphic computing, and it could reshape the future of AI. Let's rewind. Since the 1940s, our computers have followed a pretty strict formula. It's called the von Neumann architecture. Data and instructions are stored in memory. The CPU fetches them, processes them, and stores them back. Simple, logical, fast, but also fundamentally limited. Why? Because it separates memory and processing? Your computer has to constantly move data back and forth. This creates a bottleneck, especially when it comes to learning tasks. Now compare that to you. Your brain doesn't have to shuttle data between separate units. It processes and stores information in the same place across a sprawling web of neurons. Everything happens at once, in parallel, and all of it runs on just 20 watts of power, less than the bulb in your desk lamp. So scientists started asking a radical question. Why not just build computers that work like brains? Chapter 1. The birth of neuromorphic computing. The idea was born in the 1980s by Caltech professor Carver Mead. He proposed a bold concept. Stop using computers to simulate brains. Start building chips that actually mimic them, right down to how neurons fire. These weren't just new chips. They were a new philosophy of computation. And today, that vision is becoming a reality. Intel's Loihi 2, IBM's TrueNorth, the University of Manchester's Spinnaker, all examples of hardware designed to behave like biological brains. But how do they actually work? Let's break it down. Neuromorphic computing. Think of a traditional neural network like an assembly line. Input goes in. It gets passed through fixed layers. Output comes out. Powerful? Sure. But also rigid and energy hungry. Neuromorphic computing flips that. It uses spiking neural networks, or SNNs. These are modeled after how real neurons behave. They don't just pass information, they fire pulses. Short, sharp spikes. The timing and pattern of these spikes are what matter, not just the amount. That's exactly how your neurons communicate. Each spike is like a word in a language, and together, they form a conversation your brain can understand. Chapter 2. How neuromorphic chips learn. In the brain, connections between neurons called synapses get stronger or weaker based on experience. This is called synaptic plasticity. It's how learning happens. Neuromorphic chips replicate this with programmable hardware. Each artificial neuron is connected to others via dynamic synapses. These connections adjust over time based on rules like STDP, spike timing dependent plasticity. That means if neuron A consistently fires right before neuron B, the connection between them strengthens. This mimics how you remember the face of someone you see every day, or how you learn to avoid a hot stove. The chip doesn't just store data, it changes its structure with experience. Chapter 3. Loihi 2. A chip that thinks differently. Let's take a closer look at one of the most exciting breakthroughs in brain-inspired computing. Loihi 2, Intel's latest neuromorphic chip. At first glance, it might look like just another silicon wafer. But under the surface, this chip behaves in a way that's radically different from the processors in your laptop or smartphone. Loihi 2 contains over 1 million digital neurons, each one acting like a miniature version of the neurons in your brain. These are the basic units that receive, transmit, and process information through spikes, just like biological neurons do. And the connections between these neurons? They number around 120 million synapses. That's more than 10 times the population of Tokyo, all linked and firing in response to real-world data. Here's the amazing part. All of that complexity is packed into just a few square millimeters of silicon. It's like shrinking an entire ecosystem of computation into something smaller than a postage stamp. But what really sets Loihi 2 apart is how it operates. Unlike traditional CPUs or GPUs, which rely on a global clock ticking away at billions of cycles per second, Loihi 2 runs asynchronously. There's no central timer. Instead, neurons only fire when they need to. It's an event-driven system, more reactive, more adaptive, and far more energy efficient. In fact, that's one of the chip's biggest strengths. Tasks that might consume hundreds of watts in conventional processors, like analyzing complex patterns in audio, visual, or motion data, can be performed by Loihi 2 using just a few milliwatts. It's like teaching a robot to walk and having it learn in minutes on a watch battery. Chapter 4. Real-world superpowers. What neuromorphic chips can do. Neuromorphic computing sounds cool in theory, but what can it actually do? How does a chip that learns like a brain make a difference in everyday life? Let's take a look at some real-world use cases where these chips aren't just promising, they're already performing. 1. Smart sensors at the edge. Imagine a wildlife camera hidden deep in a forest. Leaves rustle, wind blows, squirrels dart by. You don't want hundreds of false alerts. You want to know when something rare walks past like a tiger or a snow leopard. With neuromorphic chips, that camera doesn't need a cloud connection or constant internet. It can learn on its own right there in the bush. It identifies patterns, ignores background noise, and alerts you when it sees something worth seeing. 2. Real-time robotics. Picture a drone flying through a dense forest, a sudden gust of wind, a new obstacle, no problem. Thanks to spiking neural networks, the drone can adapt on the fly, literally. Or consider a robotic arm that learns how to handle fragile objects, like eggs, just by watching someone once. These chips give robots real-time, on-device learning, not just automation. Adaptation. 3. Adaptive hearing aids. Traditional hearing aids just amplify everything. But a neuromorphic hearing aid? It can filter out background noise, highlight the speaker in front of you, and even learn your personal preferences over time. It's not just hearing louder, it's hearing smarter. Human brain versus neuromorphic chip. Let's put them side by side. We're not building full human brains, not yet. But we're capturing key principles that make our brains so powerful, and we're turning them into hardware. Chapter 5. Should we build machines that think like us? If we're building chips that learn like the brain, that adapt in real time, that evolve from their environment, are we still just making tools? Or are we creating something more? Neuromorphic computing brings us to a crossroads where science fiction starts looking more like science fact. Until now, computers have been calculators. Fast, powerful, precise, but ultimately predictable. You tell them what to do, and they do it. Nothing more. But now, we're building systems that don't just follow instructions, they learn from experience. They make decisions. They change themselves over time. That's not just a technological shift, that's a philosophical one. Now we start asking bigger questions. Can machines be creative? If they can compose music, write poetry, or discover new scientific ideas? Are they just mimicking patterns or truly creating something new? Should we trust them to make decisions? If a neuromorphic AI can react faster, process more information, and adapt better than a human, should it be allowed to drive cars, perform surgery, or manage financial systems on its own? Could these machines ever feel something? It sounds far-fetched, but consider this. If we mimic not just how the brain calculates, but how it processes emotions, do the lines between machine and mind start to blur? These aren't questions with simple answers. And we're not there yet. But here's the thing, every step we take toward brain-inspired computing brings us closer to that threshold. As these chips become more sophisticated, more capable of autonomous learning, contextual awareness, and behavioral nuance, the line between simulation and cognition becomes harder to define. And that's why this moment matters. Because we're not just designing new machines. We're redefining what intelligence looks like. And with that comes enormous responsibility. How do we ensure transparency in systems that change on their own? How do we embed ethics into machines that learn from the world, which, let's face it, isn't always a great teacher? Should we put limits on what machines can become? Or should we explore how far this new kind of intelligence can go? One thing's clear. The more our machines begin to think like us, the more we'll be forced to think deeply about ourselves. Chapter 6. What we all should remember. 3 key takeaways. 1. Energy efficiency. Energy consumption is one of the biggest challenges facing AI today. Training cutting-edge models like ChatGPT or DALL-E doesn't just take time, it takes massive amounts of power. We're talking about energy equivalent to what 100 average homes use in an entire year, just to train a single model. And that's not even counting the energy used every time someone interacts with it. Now imagine scaling that up across the world. The environmental footprint of AI is becoming hard to ignore. This is where neuromorphic computing flips the script. Unlike conventional chips that run all the time, neuromorphic processors like Loihi 2 are event-driven. They only process information when something actually happens. No wasted cycles. No unnecessary computation. 2. Real-time, on-device learning. Let's look at how most AI systems operate today. Typically, your device records data, say, your voice, location, or sensor readings, and then sends that data up to the cloud. There, a powerful model processes the information and sends the results back down to your device. It works, but it's slow, it uses bandwidth, and it raises serious privacy concerns. Now enter neuromorphic systems. These chips change the game by keeping the learning local. Instead of shipping data to distant servers, the chip learns right on the device, in real time. No round trips, no lag. Imagine a car that doesn't just respond to conditions, it learns your driving habits as you go, adapting its behavior to keep you safer. Or a smartwatch that detects your stress patterns, quietly improving without ever uploading your personal health data to the internet. Or a drone that senses and adapts to changing wind patterns mid-flight, becoming smarter with every second in the air. This approach brings three huge advantages. Privacy, because your data stays with you. Speed, because there's no waiting. And autonomy, because the system improves all by itself. This is the kind of intelligent independence neuromorphic chips make possible. 3. Adaptability and lifelong learning. Most AI today is brilliant but rigid. Once it's trained, it stays more or less the same unless engineers manually retrain it with new data. That process is resource-heavy and time-consuming. It's like giving your AI a complete brain transplant every time the world changes. Neuromorphic chips offer a different model, one that's more like how humans learn. They support what's known as lifelong learning, the ability to adapt continuously without needing to reboot or retrain from scratch. The chip can tweak connections, adjust weights, and reshape its internal map as it interacts with new environments. Picture a robotic assistant in a hospital. Instead of being reprogrammed every time protocols change, it adapts on the fly, learning from patient feedback, adjusting to new layouts, and refining its behavior with each shift. Or consider an industrial robot that improves with every part it assembles, getting more precise, more efficient, and even learning to avoid mistakes it made just hours earlier. This kind of fluid, adaptive intelligence makes neuromorphic chips ideal for the real world, where change is constant and unpredictable. In a way, they don't just compute, they grow. That's not just a technical breakthrough. It's a whole new philosophy for building machines that think, learn, and evolve just like we do. Chapter 7. The Road Ahead. What's next? Neuromorphic computing isn't just another step in processor evolution. It's not like moving from floppy disks to the cloud or from desktops to smartphones. It's something bigger. It's a paradigm shift, a fundamental rethinking of how we build machines, how they process information, and even how we define intelligence. Think of it like this. For the last century, we've trained computers to speak our language, rigid, logical, and rule-based. Now, with neuromorphic chips, we're teaching them to speak the brain's language, noisy, adaptive, nonlinear, and spiking with meaning only when necessary. And the implications? They're enormous. Currently, scientists are exploring brain-computer hybrids, interfaces where neuromorphic chips physically connect with living neurons. Imagine devices that help restore mobility in paralyzed patients, or chips that integrate directly with the human nervous system to treat real-time epilepsy or depression. In other labs, researchers are developing swarms of neuromorphic drones. These aren't just flying robots. They behave like flocks of birds or schools of fish. They communicate instantly, adapt to obstacles, and even learn from one another without relying on centralized control. Then there is the frontier that sounds like science fiction, but it's already happening: organic neuromorphic chips. These are processors built with biological components, like actual protein scaffolds or cultured neurons grown on silicon. Machines that are, quite literally, part organic. Why build these? Because nature has already optimized the most energy-efficient, resilient computing system known, the human brain. And by mimicking that architecture not just in form, but in function, we might uncover better ways to solve real-world problems. From real-time translation and climate modeling to autonomous robotics and beyond. Chapter 8. Challenges and limitations. All of this sounds revolutionary, and it is. But if neuromorphic computing is so powerful, why isn't it everywhere yet? Well, like any transformative technology, it comes with growing pains. First, it's still in its early stages. We're not talking about mass production or plug-and-play systems just yet. Neuromorphic chips like Loihi 2 are mostly used in research labs and experimental prototypes. The software ecosystem is also pretty limited. Developers can't just use standard coding frameworks like TensorFlow or PyTorch. They need to learn entirely new paradigms of thinking, things like spiking neural networks, event-driven programming, and real-time adaptation. Integrating these chips into existing infrastructure? Not easy. Traditional systems aren't built to handle real-time dynamic learning. That makes everything from compatibility to scaling a real headache. Then there's the issue of predictability. Neuromorphic systems learn and change based on their environment, which makes them powerful, but also harder to debug. If something goes wrong, it's not always clear why. There's no fixed model to trace back to. And finally, there's the philosophical side. What does it mean when machines learn unpredictably? Can we trust them? Should we limit them? With great intelligence comes great responsibility, and that's a whole new frontier we're only beginning to explore. Like any transformative leap, this one comes with growing pains. Chapter 9. The Big Picture. Your brain is the most complex, energy-efficient computer we've ever encountered. It operates on just 20 watts, about the same as a light bulb, yet it performs trillions of calculations, processes emotions, stores memories, and adapts in real time. No supercomputer on Earth comes close. Now, for the first time, we're creating machines that don't just act smart, they actually learn smart. Not through brute force or endless data crunching, but through elegant design, inspired directly by the architecture of the brain itself. Neuromorphic computing is the bridge between neuroscience and technology. It doesn't just help us build better machines, it helps us understand ourselves, how we think, how we learn, how we adapt. This isn't about making faster processors or squeezing out more frames per second. It's about something deeper, crafting human-centered AI that operates more like a partner than a tool. Machines that learn gently, evolve with context, and maybe hopefully carries a little more wisdom in how they operate. We're not just trying to replicate the brain's power, we're trying to honor its brilliance. And in doing so, we're planting the seeds for a future where machines are not only intelligent, but also perhaps understanding. Chapter 10. Question? If you had the chance to teach a machine that learns like a human brain, truly learns, adapts, and grows over time, what would you teach it first? Would it be kindness, creativity, or curiosity? We'd love to hear your thoughts. Drop your answers in the comments below. And if you enjoy science that not only informs but also inspires content that bends your brain in the best possible way, make sure to subscribe. There's a lot more wonder out there to explore. Thanks for watching, stay blessed, and please stay curious.